부담을 안 하시는
네.
참가자 기준 16명.
머리가 애매한
네, 안녕하세요. Good morning. So we're gonna make a start. Today we're going to continue. 네, 이거 하라 그랬죠? 이거 어떻게 쓰는 건가요? 그렇죠? 소리 안 들리는데?
여기다
치면 되나요?
네. 이게 주문을 넣으시면 되고 잘
이렇게까지. 이거 하면 좀 나아요? 똑같지 않아요?
뒤에가 좀 더 들리네.
네. 네, 시작하겠습니다. We'll make a start. So we're going to continue the introduction to speech recognition systems. So, the plan is today I'm going to finish the introduction. Next week and the week after, for about 2 weeks, we're going to talk about traditional systems in speech recognition. It's becoming less and less relevant because there's more and more deep learning now. But I think it's still important to go over the history of how we used to do the speech recognition. So we'll spend a couple of weeks on that. And then I'll make that as quick as possible because I think a lot of you will get bored. And after that, we're going to spend the first half of the semester covering deep learning basics and how to use deep learning for speech recognition. So that's the plan for first half of the semester. As we introduce speech recognition, we want to first talk about the challenges in speech recognition. There are a lot of challenges in terms of linguistics. First, even if we say the same thing, it might sound differently to you depending on where it is said. For example, in a quiet room like this, there's not much noise apart from my voice and not much reverberation. But if you're, for example, talking in a large hall, there might be a lot of reverberation. Like reverberation is a way of saying like echo. So if you say one thing, you know, it sort of echoes for several seconds sometimes. You get that sort of effect in some room. On the other hand, if you're talking in the street, you might not get much echo, but there'll be a lot of noise of cars, other people talking on the street, and so on. So even if I say the same thing, it might sound differently to you. Also, there's large variety in the number of words used. When we're writing or speaking everyday language, we actually use more number of words than you think of. So because of the size of vocabulary, this is very hard. So we have, in effect, we have a very large number of classes that we have to classify. According to some studies, the average active vocabulary of an adult English speaker is around 20,000 words. So that's a lot. If you're talking about like other machine learning problems, such as like computer vision, you're typically dealing with like 1,000-way classification. But with speech recognition, even just with one language, you're talking about 20,000-way classification. So obviously that's not an easy problem to solve. Also, everyone speaks differently. And that means even if I say something, and if I say one word, and if you say the same word, the pitch and the frequencies that I generate will be different from the frequency each of you generates. So if you're trying to classify a word based on the frequency produced, it's obviously not an easy task. And that's related to the previous problem. everyone has different speaking styles and accents. Some people speak slowly, some people speak fast, some people have accents. And even in a small country like this, Korea is a relatively small country. There is a huge variety of ways that people speak, depending on which part of this small country that you're from. So modeling this is very difficult. And even in Korean language speech recognition, we need a data set to cover all the accents from like Seoul region, from Gyeongsang region, from Jeolla region. The people all speak differently. So we need a data set to cover all of that. And even if it's the same person, depending on what mood they're in, they can speak differently. And so even if you say this is a fixed sentence, depending on what emotional state you're in, it is very different how it might be pronounced and how it might be heard by somebody else. Now, also in terms of in machine learning perspective, speech recognition is challenging. If you talk about a typical problem in computer vision, look at this on the left. One of the prime tasks in computer vision is ImageNet classification that a lot of people work on. That is, you have one image coming in, and which is a fixed dimensional input, and then you just have one output going out, which is the class. So it's one of, let's say, 10,000 or 1,000 classes. But if you're talking about a typical problem in speech, you have variables and high dimensional output. For example, if you want to classify like last 10 seconds of what I spoke, it's not just one word that I produce. It's a sequence of words that I produce. So if you talk about something like this, you can do classification at character level or word level. But no matter what sort of approach that you take, it's equally challenging because we don't have a fixed number of words. It's not just one-to-one classification. It's many-to-many classification where we don't know the alignment. And related to that is that it's a sequence-to-sequence problem where the current time step output is dependent on previous time step outputs. You might remember that we talked about ambiguity in speech recognition in the last lecture. So in the last lecture, we talked about different words sounding very similar, like whole and like whole like this, and see as in look, and see as in the sea. So if we want to write down what it is accurately, we need to know the output depending on what was the output of the previous time step. So that's not just a one-to-one transcription problem. We also need to understand what's come before and what is the output that is relevant to what has come before. And finally, it's the training data for speech recognition is typically quite limited compared to other tasks. For example, if you talk about ImageNet again, you have 15 million image examples. But if you're talking about LibriSpeech, which is the most popular data set in speech recognition, you only have less than 300,000 utterances. So if you're talking about the number of examples, the most popular data set in speech recognition, which is LibriSpeech, has 50 times less data compared to the ImageNet dataset. So obviously that proposes a significant challenge. But regardless of that, we have seen a very dramatic improvement in speech recognition performance. On the popular dataset, like the LibriSpeech dataset, the word error rate, which is basically a way of saying what proportion of the words the recognizer got wrong is down to 1.4% on the Liberty Speech Clean and 2.6% on the Liberty Speech Other, which is a bit more noisy set. But that is only on the Liberty Speech dataset. The Liberty Speech dataset is a dataset containing audiobooks. So if you're thinking about audiobooks, it's not everyday conversation. Audiobook is recorded in a perfect studio environment, and it's done by professional speakers. So it's spoken as clearly as possible. But let's look at the performance on other datasets. For example, call home datasets, that is slightly more difficult because this is telephone conversations between family. So you're talking in a comfortable way. You're not a professional reader who's reading a book. You can say anything that you want, and you'll be speaking in colloquial language. So in that, the word error rate, the state of the art, is 11%. On the other hand, let's look at the Chime dataset. The Chime dataset here is dinner party. Here, just as in the call home dataset, you're not speaking something scripted. You're talking freely. But the difference between the call home dataset and the Chime dataset is that in call home dataset, you have a phone to your face like this, and you're talking directly to it. So the quality of the recording is probably quite high because you have microphone right next to your face. On the other hand, if you are in a dinner party, you often have multiple people talking at the same time. So you have a lot of noise. You might have noise from the kitchen, and you have two options. Here you have the body-worn microphone, which is probably something like this. So the quality of the recording is a bit better. There, the word error rate is 47%, which means you're only getting half of the words properly recognized. On the other hand, if you have Chime 5 dinner parties in a data set with distant microphones, so for example, I'm talking here, but you're recording from over there, then the word error rate is 81% using this relatively state-of-the-art model. And that's a problem because you're only recognizing one out of 5 words correctly. So if you're trying to record with lots of noise from far away, speech recognition is a very hard problem. So although if you look at data set like Liberty Speech, it might look like speech recognition is already a solved problem. It is not. If you're looking at some more challenging data sets, we still have a long way to go. In building ASR systems, there's been dramatic improvement in performance over the last few years. If you look at the state of the art, the switchboard dataset, which is one of the telephone conversation datasets, the performance has improved from 16% to 6%. A lot of you, there are a few people from my lab, so they'll be working on speech, but from other labs, you'll never come across building a speech recognition system, ASR systems. But even if you don't build an ASR system, you might often, when you're doing experiments, you might have to use an ASR system. For example, if you're working in NLP or something, if you want to make a conversational system, you might just get an ASR system off the shelf, like for example, Google ASR system, and then connect that with an application that you want to use. But I think it's, even if you're not going to build an ASR system, it's useful to understand the ASR system. So you understand what types of errors are easy to correct, why they occur, and how a downstream system, such as a conversational NLP system, how can they make use of uncertain outputs. Also, your question might be, there are a lot of good ASR systems out there. Like Amazon has a public API you can pay to use. You might pay, like, for example, 2 cents per query you send. And there are a lot of them. But if you're building a speech recognition system for your particular application, then you can, if you're training your own system, you can customize to your own target domain. For example, you might just use Amazon API for everyday conversations, but let's say you want to record and recognize conversation like this. We use a lot of specialized vocabulary because we are in a lecture with a lot of technical terms. If you use a regular speech recognition system for this, it's not going to work very well. And that's because it's not used to the kind of vocabulary that we use a lot. So if we build our own system, we can put more training data that's applicable to our domain. So we can get a speech recognition system that builds, that's good for what we are trying to do. ASR is also a key part of dialogue systems. When we say dialogue systems, we might look at something like this. At the start, you might have an ASR system, which converts what we spoke into words. And then the next part is understanding the words that was produced. So if you look at this, it basically gives probability of what was said. And then from what was said, then you can parse it into meanings. And that's called spoken language understanding. And then you can do a dialogue state tracker and dialogue policy. So you can make a set of rules to produce what to output based on the intention of the human. And then having produced the sentence using natural language generation, the last part of a conversational dialogue system is text-to-speech, getting the text back into speech. This course is about speech recognition. So we'll be focusing on this part, listening to what a human said and converting that into words. The definition of speech recognition is simple. You're converting a waveform into a sequence of words. So from X, which is the signal, you can produce the sentence, which is what is the weather today. But you can split this into two ways. First, there's the batch, so which is basically you're putting in one or multiple utterances as a batch and passing that to the neural network, for example, and getting the whole sentence back at the end at the same time. So for example, this is equivalent to if you have a speech recognition system, you just drop a WAV file and you get a result in one batch. You just one WAV file goes in, one sentence comes out, or one sentence or multiple sentences, in fact. But there's the other option, which is streaming. In streaming ASR, you use this when you need to get the sentence back in real time. So before you complete the sentence, when you complete a word, you might want to hear the word in real time. So you put in a small chunk, and that's how, and it comes like this. You put in a small chunk, and you get the output bit. Anyone in the class, when would this be useful? When can you use batch format, and when can you use streaming format? Any raise of hands? What sort of application would be good for the batch format, and what sort of application for the streaming format? Anyone? Or when do you have sense of urgency like this? Word by word? When would this be useful? I think for streaming, for example, this might be useful if we're doing live TV captioning. If you're looking at live news and you want to follow quickly what's being said on TV, the streaming might be useful. On the other hand, if you're doing charting of doctor's conversation, or if you want to record what was said in a meeting, it's not so urgent. So you can put it in a batch format. And the architecture that you use for batch and streaming is different, but often in order to produce a streaming system, you sacrifice accuracy or speed. So it depends. If you have no urgency, you can use batch system for more accuracy or more efficiency. Or if you need the transcription quickly, you might use a streaming system where it has to listen to your conversation all the time to produce what was said, return the words immediately. You represent the input X. Here, you remember what X and Y, X and W are? You represent X as a sequence of feature vectors. What's typically used is 257-dimensional spectrograms or 13-dimensional MFCC vectors. Spectrograms we'll talk about at the end of this lecture. MFCC we'll talk about next week. But instead of feature vectors, in these days with the advance of deep learning, now often we use, rather than spectrograms or MFCC vectors, we use raw waveform, which is exactly directly what is recorded by the microphone. Typically, what's recorded by the microphone is 8,000, 16,000, or as high as 44,000 samples per second. So it's a very high dimensional input. But we often still use in very modern systems with the advance of computational power and deep learning algorithms. Now, representing the outputs. The output is represented as a sequence of sentences, words, or characters. But in reality, we often use characters. It's rarer to use words. And in fact, it's very rare to use sentences as an output format of speech recognition systems. And that's because, can anyone think of why we don't do sentence classification in speech recognition? Why do we classify in small chunks like characters or words rather than sentences?
Because of the high dimensionality. So many classifications like output.
Yeah, we would have a very high number of classes if we have sentences. Because, for example, when we look at characters, we only have 26 characters in the English alphabet. And even the 26 characters, if we have 26 characters, we can add like space and blank token and a few other bits and pieces and numbers, then we might have 40 characters. If we have words, we just said that we might have 20,000 words that people might typically use. But if we're talking about sentences, like there are so many combinations that can you can use words to produce sentences. So if you think about the kind of sentences you can use, you might use, like, for example, like 10 million different sentences. So because there are too many possible sentences that you can use, we typically don't do sentence classification. We do character classification or sometimes word classification, but that's more rare. So to define the problem that we're trying to solve in speech recognition, X is the sequence of acoustic feature vectors and W is the word sequence. And we're trying to find the most likely word sequence W star given by the following equation. So we're trying to maximize the probability, we're trying to find the maximum, we're trying to find W that maximizes the probability given the input acoustic feature X. And there's traditional and end-to-end approaches to ASR. Traditionally, this is the fundamental equation of statistical speech recognition. This is the same equation I gave earlier. The most likely word sequence is given by this equation. And by applying the Bayes rule, you can expand this equation into this equation. So this equation, first equation, is called the acoustic model. That relates the words, the characters to the acoustic features. But we can then split the probability of W. So this has nothing to do with the sound, which is called the language model. I'm not sure, there are probably many of you who actually specializes in NLP who would know this part, the language model part, much better than I do. But by splitting ASR system into acoustic model and language model, we can get a lot of benefits. For example, the language model here can be trained on a lot of data without text, without sound. So the language model, this part, can be trained on text-only data, for example, Wikipedia. And by doing that, we can produce, we can basically help the ASR system by saying how likely this sentence output is. So for example, even if a sentence might sound like, please move to the right, as in WRITE, please move to the right, that makes no sense, right? It's please move to the right, as in RIGAT. So a language model will tell you, without the sound, that please move to the right is more likely than please move to the right. So this sort of helps you produce correct probabilities on what the output might be. And typical traditional speech recognition system might look like this. You have the first X recorded speech, and you do some signal analysis, which is some feature generation. So here you might produce MFCCs or other feature vectors. And then you have two models. You have the acoustic model and you have the language model. And using that, you search all of the possible spaces W, and out of the W, you find the most likely word or sentence, which is the W star. So this is the typical part of speech recognition. The signal analysis part to produce the feature vectors that we'll talk about in the next lecture, which will be on next Tuesday. After that, next Thursday onwards, we'll talk about hidden Markov models from which we generate the acoustic model. This is the basic components of traditional speech recognition system. But when we do end-to-end speech recognition, we often combine all of this into just an end-to-end ASR model. Here you see that you may or may not have signal analysis. End-to-end ASR models can take MFCCs, but sometimes you can put in raw waveform. You don't have acoustic or language models, although you can have independent language model with end-to-end ASR on top. But often with the end-to-end language model, the implicit language model is built into the ASR model. So often that's not required. So we replace all of these subcomponents into an end-to-end model, and we'll practice generating this in the second half of this lecture by going through practicals. So this is the traditional ASR model compared to the end-to-end ASR model. And when we train an ASR system, we have a problem, which is that we have typically it'll be really good if you have a data set saying that's segmented into words or characters. But usually it's not like that. When we have in a sentence, we might have a file called one dot wave, which contains a whole sentence. How is the weather today? But this one dot wave you don't know which part of that wave file corresponds to how and which part of wave file that corresponds to weather. You just know that somewhere in this wave file, there's the word weather. Well, we don't know where in this file the weather is. So labels are usually given at utterance or sentence level. Labels are rarely given at word level or character level, but we're trying to do recognition at word or character level. So it's not as simple as just straightforward classification. Then we have to do alignment. There are multiple ways of doing alignment. What alignment is basically segmenting the sentence into which part of the sentence corresponds to which part of the features. So we don't know if if this recordings is no right. We don't know which part of the input feature corresponds to no and which part of the input feature corresponds to right. It could be this, it could be this, we don't know. So we need to find the alignment. We're not going to talk about how to do this today. Again, we're going to talk about the solutions to the alignment problem throughout this course. But there are multiple ways of doing this. Traditionally, you can use hidden Markov models. Using deep learning, you can do connectionist temporal classification, which is often called CTC. It's a popular way of doing alignment in speech recognition. Or using more modern architectures, you can align the features using attention. That we'll talk about last. And during inference, when performing decoding, it is hard to search over all of the input space W, because we talked about in a sentence, there are almost infinite number of combinations that can produce the word or sentence W. So rather than doing a full search over the space, we often do a beam search in order to limit the search space. Again, this will be described later in the course. This is a method to make sure that you don't have to search over all possible combinations of words or all possible combinations of characters to find which is the most likely word or which is the most likely character. Yeah, so I'm basically covering what we have to cover in this semester. And we have to evaluate how well we have produced a sentence. In order to evaluate the accuracy of speech recognition system, we used something called string edit distance. The string edit distance is the sum of insertion error, deletion error, and substitutions. Who has heard of edit distance here? Raise your hand if you know what an edit distance is. Not many of you. Okay. The edit distance can be at word level or character level. If we're talking about word edit distance, that means how many words you had to substitute or delete or insert to produce the target sentence. If we're talking about character edit distance, is how many characters you have to replace, insert, or delete. So, and character error rate is known as the substitution plus deletion plus insertion. So here the numerator is the edit distance divided by the number of words in the ground truth. So here, if you say steal or team or stream instead of the steam, which is the answer, the steam is the ground truth. All of here, the edit distance is 1 because you have to change one thing, delete or insert or substitute one thing to make this become the ground truth, divided by 5. So here the edit distance is 1 and the ground character error rate is 5 for all of them. Here, if your answer, the ground truth is intention, and you produce execution, the edit distance is 5, because the smallest number of edits you can do to make execution become intention is 5. You have to delete one thing, you have to substitute 3 things, and you insert 1 thing. Just to make sure you got the concept, just here try finding the answer to this problem. What is the, not character array now, we're talking about word arrays. What is the word array of the first one, the second one, and the third one? Can you, if anyone's calculated the word array of these 3, can you raise your hand and give me an answer? If you're on Zoom, you can type on Zoom chat if you have the answer. Anyone answer to the first part, what is the word array? I think that's an easy one, so you should be able to give me an answer straight away. In percent. What is the word array in percent? Nobody? 50%. That's correct. How about the second one? Actually, the second one, if you don't have a language model, you'll make a problem error like this a lot, because the maid and the maid sounds very similar. The hotel maid made the bed. What's the word array here? What's the minimum number of operations you need to do to convert prediction into ground truth? Yeah, somebody on Zoom answered 34%, which is basically right. You have to do 2 operations to get to make this. So you need to substitute this with this and this with this. So 2 operations. The length of the ground truth is 6. And the last one is the answer. The ground truth is portable phone upstairs last night, and it predicted preferable form of stores next slide. What is the word array here? Nobody? I have an answer on Zoom, 120%, which is correct. Actually, you have to change everything to get this from this. And you actually need 6 operations to convert this sentence into that sentence. So if the length of the ground truth is 5%, 5 words, and the operations you need is 6. So you need 120%. So you can have a word array over 100%. It was just to tell you that. Now, in the last part of this lecture is we're going to talk about how we produce speech. Speech production starts from the lungs. It starts here, and basically the air is pressed out of the lungs through a route like this, as you see in the, and it continues. It comes up here, it goes past through the vocal folds, and it continues through the vocal tract and exits through oral and nasal cavities. Oral cavity is basically a way of saying your mouth and your nose, and that produces speech. And the position of the articulators, that's the position of your lips, of your jaw, of your tongue. This alters the shape of the vocal tract. So the vocal tract is here, and that produces different sounds. If you think about it, when you speak, you move your lips, you move your jaw, you move your tongue. And all the combination of that produces the phone that you want to produce. And we want to model the speech production process. And we can model it a bit like it's a bit like blowing air through bottles. The depth and the shape of the bottles create different resonance. If you ever try to blow through a glass bottle, you know, it creates a certain frequency. And depending on the shape of the bottle, how deep it is, how wide it is, it produces different resonance. It produces different frequency. So it's just like that. It's like blowing air through bottles. And if you summarize the speech production process, basically air goes through the lungs, and it goes through the vocal folds, which makes a vibration, which makes a wide range of frequencies. And the shape of the vocal tract is like a filter. It puts a filter on these frequencies. So it amplifies certain frequencies. It absorbs certain frequencies depending on the shape of your tongue and shape of your throat and shape of your lips and so on. And that produces the final sound. And it produces the different resonant frequencies are produced depending on the shapes of the vocal tract. And these frequencies are called formants. And these formants can be useful to detect basic sounds called phonemes. And we have with the formants consists of multiple frequencies. Speech signal, if you record, it looks like this. The signal is composed of many frequencies, and it looks like this. So if you put a frequency plot of your voice at a particular point, you have multiple peaks like this. This is frequency, and this is the power at that frequency. So you might have a peak here, and peak here, and peak here, 3 peaks. And the signal is composed of many frequencies, which is called F1 and F2 and F3. This is called a spectrogram. Spectrogram is, this is time, and this is frequency, and the energy is color. So red is a lot of color. A bright red, red and bright means a lot of color, and black and dark means not much. That color means a lot of energy at that frequency and time. And this means the black and dark means not much energy. So here you see 1, 2, 3 frequencies. Do you see that? At low frequency and around 1000 kilohertz, there's a lot of energy at this time. And around like 1.5 kilohertz, there's also a lot of energy at this time. And it's representing the same thing as this. So here you see a lot of energy at here, here, and here. But the difference is this plot is at a particular time. So this represents one time. So here, because the second axis became color, so one column of this, like this, represents one time. So this represents energy at different frequencies and different time. And the energy now is color. So this, you see 3 frequency, and we call this from bottom F1 and F2 and F3. If we go back here, this is F1 and F2 and F3. And this is what determines the phonemes or phones that you're trying to pronounce. F1, F2, F3 values, this is time. So values, and this is frequency plot, change over time as phones change, and as shown in the spectrogram. And this changes over time because the shape of your mouth and shape of your lip and shape of your tongue is changing over time as you're trying to pronounce different things over time. And pitch varies by people. The pitch is not important in speech recognition. The fundamental frequency, which is produced down here, is called F0, and that represents the pitch. that's not important in speech recognition, although it might be important for speaker recognition that we'll talk about later. In speech recognition, the F0, which is the fundamental frequency that determines the pitch, is not important in speech recognition. So here we're looking at F1, F2, and F3, and so on. And F1 and F2 and F3, it does vary by people, but the relationship between them represents what sort of vowels that you're trying to pronounce. So for an average male, for the F1 and F2 values for I is 240 and 2400 hertz, whereas for, let's say, this 600 and 1900. So there's a lot of difference in frequencies produced by different vowels. And these formants, F1 and F2 and F3, they represent different phones. I'll talk about what phones are in a minute, but we have phones and phonemes to represent a small structural unit that distinguishes meaning in a language. For example, there are about 40 phones in English, and these are the key phones that we use in English. For example, they might learn that the word dog is made out of 3 phonemes like these. Phonemes are different from alphabet. So the word dog consists of this phoneme and this phoneme and this phoneme. A phoneme is the smallest structural unit that distinguishes meaning. Phonemes are not physical segments, but they're cognitive abstractions or categorizations of these meanings. And phonemes are typically transcribed inside slashes like this. On the other hand, phones represent the instances of phonemes in the actual utterances. So the phones are the actual sounds that you produce. So the phones represent the physical sound segments, and the phone is a speech sound that you produce. The phones are typically marked in brackets like this, and many phones might represent the same phoneme. The phoneme is a part that's stored in your brain. And when you actually produce a sound, you're producing a phone. So you think about producing a phoneme, and you end up producing a phone. So that's the relationship between phone and a phoneme. Phone is the actual sound, phoneme is the abstraction that you're trying to produce. Now, just to finish, the sound is recorded by a microphone. The microphone records amplitude over time, not frequency. So if we're interested in frequency, because it's the F0, F1, F2, F3 that we're interested in, we're not really interested in the amplitude. So we often convert amplitude into frequency. And how we do that is using STFT, short time Fourier transform. And we do STFT to convert amplitude into convert this into a spectrogram like this. The exact process of STFT we'll talk about in the next lecture, but because frequency is more relevant to detecting the phonemes, we use spectrograms. The spectrograms represent speech content, frequency content in the audio as colors in the image. And to plot the spectrogram, we do STFT for each chunk. So we do Fourier transform, Fourier analysis of a short chunk, and we do that for multiple chunks to produce the spectrogram. And for each chunk, a vector is produced. The dimension of the spectrogram is the number of chunks that we make. For example, if we make one chunk for every, let's say, 10 milliseconds, for a 1 second segment, we'll have 100 chunks if we're moving 10 milliseconds at a time. And the dimension of the spectrogram is the number of chunks times the feature dimension, which is typically about 257 or some other number. The spectrogram looks like this. As you see, the color is the intensity, the amount of energy at that time. And y-axis is the energy, frequency, x-axis is the time. So we call this the spectrogram. Yeah, and as I said, horizontal axis is time, vertical axis is the frequency, and the color is the amplitude of energy at that time and frequency. Looks like this, and we can generate frequency spectrogram in real time, just like this. And interestingly, some people claim that they can read from spectrograms. I'm not sure if that's true or not. Some people say if they look at the spectrogram, they can read what sort of sound it is. I'm not sure if that's true or not, but some people claim that. The spectrograms are used by most ASR methods, but with the advances in deep learning, sometimes they use raw waveform. So what's recorded from the microphone directly at 1600 samples per second or 44,000 samples per second. Some these days, sometimes you put that in directly. So not all ASR methods use spectrograms anymore. There are other features you can use in speech processing. You can use MEL spectrograms, MFCCs, PLPs, etc. And these are often used in speech processing. I'll go through MFCCs in the next lecture. And I'll finish here so we can talk about how to produce that on Tuesday next week. Do you have any questions? 질문 올라온 거 있는데 강의 자료는 어디에 올라오나요? I'll upload this on KLMS after the lectures each week. Any other questions? If not, thank you for coming, and I'll see you next week. Have a nice weekend.